So in this series of slides, there are only 3 this time, we're going to use the basic equations that we've developed to see how reflections arise. So what happens is we have an incident wave traveling down the line and it gets reflected back. So in that equation that you can see there, you get Vs, the phasor voltage, is the sum of the incident and reflected waves. And you can, by substituting in, you can see that we have a wave incident with amplitude V0I decaying in the z direction, and it's moving in the direction of increasing z, and a reflected wave with amplitude V0R. It's also moving now in the opposite direction, so it's e to the alpha z, and it's also moving backwards, so the exponent is e to the j beta z, and that's all something we've seen before. When this wave is reflected, it's due to the impedance mismatch between the transmission line impedance and the load impedance ZL located at z equals 0, which is at the end of the line. So let's see how this comes about in the next slide. So there's the figure, and we have the permissions. So you can see the VI, the incident wave with the upper blue arrow, and it hits the load, which in general could be a complex impedance. And because there's a mismatch between Z0, the characteristic impedance of the line, and the load, you get a reflected wave VR. In order to understand this, we have to look at what's happening at the load, look at the voltages and the currents. Then we'll substitute one for the other, and we will do the algebra. I'll do it on the board for you. So let me go through the equations. At z equals 0, all those exponentials disappear because they're e to the 0, which is 1. So your load voltage is the sum V0I plus V0R, the amplitudes of the incident and reflected voltage waves. The currents is the incident and reflected currents at z equals 0, and we always know from our analysis before that while the incident amplitude is in phase, that is sitting in front of the incident wave, the reflected has a minus sign. So that's seen in that the third line of the equation. I at the load is equal to 1 over Z0 V0 I minus V0 R. Those are the currents. But that's also equal to VL over ZL, which is, we know from the top equation, the sum of the voltage amplitudes incident and reflected. And now what we want to do is solve for that amplitude ratio V0R over V0I. So I'm going to do that explicitly on the board so it's not magic mystery. So IL is equal to VL over ZL, which is equal to the voltage at the load divided by the load impedance, but it's also equal to the current. So that's 1 over Z0 V0 I minus V0 R. So that's what we have. Now we cross multiply, so this times Z0, that times ZL. So we have that Z0 times V0 I plus V0 R equals ZL times V0 I minus V0 R. Now, what we do is we divide by V0 I. So we're going to get Z0 into 1 plus V0 R over V0 I equals ZL into V0 I minus, oh, that's supposed to be 1. We're dividing 1 minus V naught R over V naught I. So there we have it. And this quantity here, we're going to call gamma. That's the reflection coefficient, the ratio of the amplitudes of the reflected voltage to the incident voltage. So clearly gamma can't be in magnitude bigger than 1. You can't get more reflected voltage than what you put in. So now it's just a question of solving this equation. Z naught 1 plus gamma equals ZL into 1 minus gamma. So we can take the ZL over to the other side. We're going to get Z naught minus ZL. This isn't very exciting, I know, but it's good to see it in longhand once. So we get minus Z naught gamma minus ZL gamma, which is obviously minus Z naught plus ZL gamma. And we can take the minus sign, and that flips this around, and divide by Z naught plus ZL. And we get that gamma is equal to ZL minus Z naught divided by ZL plus Z naught. Now, in general, ZL and Z naught could be complex, so gamma could be complex number, the ratio of those two. Notice that if ZL and Z naught are not the same, you're going to get a non-zero number here. That means some of the energy is going to come back. So now we have our first encounter of how reflections occur, and this can be used over and over again in many different situations. Waves hitting metals, wave hitting glass, waves hitting glass plates, waves in 3 dimensions. This is a really very important result, and it's, as soon as I erase it, we will look at the summary equations. So we'll just spray this. So one of the hazards of working with this light board is you have to invent clever things to say while you're erasing it. I don't have any clever things to say right now because my brain is so focused on giving you the most accurate presentation. And we'll see it shortly. So once we have the reflection, we also must have the transmission. And this is all shown in the next slide, which is now ready for display. So there you have it. That's the result that we just obtained. It's equation 73 in the text. And now what's transmitted is the amount of voltage that goes to the load in a ratio to the incident voltage. So that's given in the middle equation. It's called tau. So tau is VL over V naught I. And since VL is the sum of the incident reflected voltages, and you divide, you get in the numerator V naught plus the reflected voltage, which is gamma times V naught I, and then you divide by V naught I to get the ratio, and you get that tau equals 1 plus gamma. What we're going to do in class is compute the reflected power, the transmitted power, and then interpret the result of the voltage and the current expressed using gamma involving the incident and reflected waves.